Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 83 in our incredible new tutorial series where you're learning how to think like an engineer using the Arduino Uno R4 Wi-Fi. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Sunfounder Elite Explorer Kit. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot simpler if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to teach you how to take those three gyro measurements, the gyro measurement measuring rotational velocity around the x-axis, around the y-axis, and around the z-axis. Take those three rotational velocity measurements and calculate the roll, the pitch, and the yaw of your MPU6050 board. Okay, sound good? I hope it does. This is actually the homework solution, my homework solution to the assignment that I gave you in lesson number 82, and I'm just curious if you guys were successful. If you were successful, leave a comment down below. I am legend. Double chest bump. And if you were not successful, leave a comment down below. I folded up like a cheap Walmart lawn chair. Now, hopefully, a lot of you guys were able to do it because I gave you some pretty big hints and I showed you how to make the measurement already on those gyros. So all you had to do was take rotational velocity and then turn that into a rotational angle. Okay. Now, let's see here. Let's jump right in and let me get out of your way. Let me have a sip of coffee. And then let me come over, and I will need you guys to fire up a browser and go to the most excellent www.toptechboy.com. Then you're going to use this happy little search tool, and you're going to search on this using Arduino and MPU6050 to measure rotational velocity with the gyros. So search on something similar to that and you'll come to this page. You can see we have the GY87 board, which has the MPU6050 module on it, and hooking it up just VCC to 5 volts, ground to ground, SCL to SCL, and SDA to SDA. So pretty easy to get hooked up. We don't want to develop the code completely from scratch, and so we are going to grab this code from last week. Now, I should say a couple of things about this code. One is we still have in this code the calculation of roll and pitch from the accelerometers. We're going to keep that because we'll use that in the future. It's just we're not going to print that today. We're going to be doing the calculation. Now we're going to add to this code calculating roll, pitch, and yaw from the gyros, and we're going to add that, and that's what we're going to print out. But we're going to keep those other calculations because before this whole thing is over with, we're going to be using all 6 sensors. So we want to carry along that old code as we move forward. Okay, guys, did you all find any surprises along the way as you were trying to get this work? Leave some comments maybe about some challenges that you faced or some things that you learned about the gyros as you were trying to make this assignment work, and then we'll kind of run into those things as we go through the code as well. So let's we got our code. Let's come over here to our Arduino IDE. Let's paste it in, and now what we're going to do is we're just going to run this to see if the universe is in proper working order and if we can have an early success by being able to copy and paste. Okay, we got to take the successes in life where we can get them. Okay, that is going. and we are downloading, and we are going to hit our serial monitor and our serial plotter. There it is. So now I'm going to let you see the board. And now what I'm going to do is, let's see if we're measuring rotational velocity. So I'm going to go about Z. So this should be the green curve. Yep. I'm getting green. And now I'm going to go about the y-axis. So this should be red. Yes. Okay, you see, I can see the rotational velocity. And now about the x-axis, and yes, the blue, we're seeing it. And then what I really love is that just goes back, no noise, beautiful zero signal as we're doing this. And so we're getting very, very cleanly, we are getting the rotational velocity. All right, now, how do you go from rotational velocity to rotational angle? So like if I come here and watch, I'm going to tilt to 45 degrees and I get that rotational velocity while I'm moving, and then the signal goes back to 0. What do I want to read here? 45 degrees. Okay, how do we do the calculation? Well, simple-mindedly, like if you're going 60 miles an hour for 2 hours, how far did you go? 120 miles. Okay, so that's 60 miles per hour times 2 hours is 120 miles. 60 times 2, 120. Okay, so that's pretty straightforward. Well, rotational velocity is the same way. If I'm going 5 radians per second for 2 seconds, how far did I go? I went 10 radians. So it's sort of like the angular velocity times the time gives you the angle that you're at. So it's pretty straightforward. But now, what is not as easy as going 60 miles an hour? Well, the thing is, if you see, this isn't a constant value. It's a constantly changing value. So the way we do this is we integrate. We take the present velocity, and then we take the little time slice between this measurement and the last measurement, that tiny little like millisecond time slice, and we measure the rotational velocity times the delta t, the dt, the time change, and then we add that to the angle before. So it's like we're integrating up that curve is what we're doing. In fact, we really are. We're integrating. We are digitally integrating. That is what we are doing. And so how would we do that? Let's come over here and let's come back over here and let's see what things we are going to need. We're probably going to need some new variables up here. Now, you remember, okay, here's our GX, GY, and GZ. Those are the rotational velocities, right? Well, what we're going to need now is we're going to be calculating roll, pitch, and yaw. And so I'm going to do a float, and I'm going to say roll. Well, remember, we're already calculating roll from the accelerometer, so I'm going to call this roll G. And so that's the roll that we get from the gyro. And I'm going to set that initially equal to 0, because when we start calculating it, we're going to be integrating up. So we need a starting value of 0. Float what? Pitch G is equal to 0. And then float yaw G, and that's equal to 0. Like that, that's pretty good. All right, now also I think that we probably need to get we need to do an int, and we need to get a t start, and we're just going to go ahead and set that to millis, and that gives you like the milliseconds that have elapsed since you plugged your board in. Okay, so you have to take this and you have to subtract. The time makes sense if you go from 2 distinct points and subtract, and that'll make sense in a minute, right? We got to get that dt, that delta t, that change in time. The present time is milliseconds. We subtract the old time, and then that gives us the dt. But I'm just putting something in there right now so the program will behave well. And then I think that what I will need to do is actually, I'm going to put it in here again, because I've got to have that first t start time, and I want to do that outside the void loop. And so what I'll do it is just the last step of the void setup. I'll snag me a kind of fresh t start time. So t start is equal to millis, like that, and then like that. Okay, why do I need to put it here? If I put it here, then it's going to do it every time, and I really want to do the real one at the end, but I've got to have an initial one, so I'm just going to put it here, and that's about as good as I can do. Okay, so now I have a t-start millis, and now I have an AX, an AY, an AZ, and then I have a GX, I have a GY, and I have a GZ, and now this is where the magic is going to happen. Okay, this is where the magic is going to happen. And right here, man, I end up with a whole bunch of blank lines, don't I? Too many blank lines. That's about right. Now I'm going to calculate roll G. Well, what is roll G? Roll G is whatever I was before. Like if I was here, I'm going to start here and go up. Or if I was here and the rotational velocity was negative, I'll start here and I'll go down. But I'm just ratcheting up, integrating up and integrating down. So it's always based on where I was before. Now the accelerometer is an absolute measurement. You look at that gravity vector and you calculate based on the gravity vector. You don't care where you were before. You don't care where you're going next. You're only in the moment what that gravity vector looks like. But here, the only way I can know where I am is to know where I was the last time. So it's going to be roll G is roll G plus, and I am going to say plus the delta time. What is the delta time since the last time I went through? Well, it's the present time, millis, minus the t start time, and that'll be the delta. Now what I better do right now is I better go ahead and get my new t start afterwards. T start is equal to millis, like that, and then when I go back around the horn, I'll have a fresh t start. That I start the stopwatch here, I go all the way through the loop and back down, and then I use it here. And then what is millis minus t start? That is the amount of time precisely that it took to go through the loop one time. That is your delta time. That is your dt. That is the little increment in time that you multiply by your present rotational velocity. Okay, so now what is the problem? This is in milliseconds. And what does the gyro report? Degrees per second. So we can't be mixing millis and seconds. So I better convert milliseconds to seconds. And I do that by dividing by 1,000, okay, times GY. Okay, now what would this be? All right, this would be the rotational velocity in y times the dt added to where we were before. We were here before, and let's say I go 1 radian a second for 1,000th of a second, then I move 1,000th of a degree. You see, it's just kind of like distance is rate times time. The incremental angle is the incremental time multiplied by the rotational velocity. The actual angle is the old angle plus the incremental angle. If that didn't make sense, stop and think about it. Now, what's the problem? I'm a degree man, and this is in radians, so I need to convert to degrees. So what do? I am going to make sure this doesn't run off the screen. I am going to multiply by 360 degrees, and then I'm going to divide by 2, or I'm going to divide by 3.14, and I'm going to divide by 2 pi. Okay, so that is divided by, I'm going to put that the right way, like I say it, divide by 2, divide by 3.14, like that. Okay, so that is roll G. I'm going to look this over. Roll G plus millis minus t start divided by 1,000. That's dt in seconds now times the rotational velocity in y converted to degrees. So that looks pretty good. Let's get this. And you can imagine that pitch is going to be almost the same thing. So the pitch is going to be the pitch, P-I-T-C-H, and then this will be G what? This will be GX, right? That's the one that goes forward, and so pitch is this way, X is this way, so pitch is rotation about X. All right? That looks pretty good, doesn't it? What else do we need to do? We need to do our friend yaw, And the yaw G is going to be equal to the yaw G. And then this is the rotational velocity around the z-axis. Man, I hope you all have seen all of that. I hope I didn't block you out of any of that good stuff. Does that look good? All right. We better put a semicolon on the end of that. All right. Then we get our fresh new value here. Okay. Could it really be that easy? I think we're going to have to print some stuff out now. And man, let's see, how many things do I want to print out? I want to print roll, I want to print yaw, I want to print pitch, I want to print GX, GY, GZ. So let's see, I'm printing GX, I'm printing GY, I'm printing GZ, and then a comma, and now I want to get roll, pitch, and yaw. So I better come down here and copy like, well, let's just say that this was roll, roll, comma, pitch, pitch, comma, yaw, yaw. And so I think that if I just copy all of these, I'm going to copy. So I got from the X to the Z, that's 3 data snippets, and then I'm going to paste. And then this GX, where we come up here to GX, this is going to be roll G, and make sure that's what I called, roll G, pitch G, yaw G, and up here, roll G, pitch G, yaw G. Yeah, I just want to make sure I'm using all my variables the same. I haven't made a change there. Okay, so that's roll G, the label, roll G, the variable, and then this is going to be pitch G, the label, then this is going to be pitch G, the data, and then this is going to be yaw G, the label, and yaw G, the data. Yaw G, the data, like that. Then we've got our comma, and then we go upper level 5, lower level -5, and let's just go 45 here. Okay, so we'll go 45 to -45. I won't tilt that much. And now what we want to see is we want to see not just a rotational velocity, but we actually want to see now we want to see an angle, roll, pitch, and yaw. Okay, so let's run this thing. Where did I leave out? Where did I leave out a colon? I was expecting a... Did you guys see where I left out my semicolon? This is nonsense there. All right, that was nonsense. Okay, let's try it again. How did I put 2? How did I put 2 there? Looking interesting, looking like we might download it. Okay, so now let's look here. All right, so I've got like a flat error there. That is kind of strange. What is that X? That is gyro X is reading kind of a large and peculiar number. GX, GY, GZ. Okay, this is very strange. Let's see if we can figure out what I am doing. GX, GX, comma, GY, GY. And that's nice and clean, right? GX, GX, GY, GY, comma. I bet I have a print line in here. Do I have an extra print line in here somewhere? No, I don't. Let's see if we look at it on the serial monitor. Okay, the GX it's reading is 30, and then I've got that. That is really strange. So let's just make sure there's not any nonsense going on. So I'm going to unplug it and plug it back in. Okay. So somehow what we had done is we kind of locked up that gyro, and do you see how I was getting a crazy reading on that of 30? And so sometimes you just got to take the power off and put the power back in. All of these little connectors like this are not the best way to do it. For the SCL SDA data, you kind of would like more secure connections than that, but that looks a lot better. So now we're going to come here, and now we are going to move this back to where you can see it. Okay, so now I've got the rotational velocity X, Y, and Z, and then I've got roll, I've got pitch, and I've got yaw. Okay, so let's try a roll. Okay. And what I see is I see the rotational velocity. Let's try a yaw. Do you see that you see the rotational velocity? And those rotational velocities look good, right? Like I'm getting up close to 5, what I was before. But how come my integration isn't working? That the roll is flat out 0, the pitch is flat out 0, and the yaw is flat out 0. Now, how could that be? Roll started out as 0, that's true, right? The roll G, the pitch G, and the yaw G, they started out as 0, that's true. But then if you look down here, I'm taking, where is that? I'm taking millis the time minus the last time through, so that can't be 0. That's a number. And then gy is a number because I can read it down here. Gy is a number. So a number times a number added to the old value. I'm sitting here and I'm just stuck at 0. Someone tell me what's happening. Someone tell me what's happening. All right. This is a classic Arduino problem. And I can't tell you how many times this bites people. And it is the hardest problem to figure out because the code looks so right. The code looks so right, and it doesn't work. Okay, it doesn't work. Now, this is what I'll tell you. Okay, millis is reported in what? It's an integer. T start was a what? You read it as an integer, so it had to be a what? An integer. So what I want you to see is millis is an integer, T start is an integer. What is an integer minus an integer? It's an integer. Okay, and then what is 1,000? 1,000 is an integer. So let's say it takes 5 milliseconds to go through the loop. This would be 5 milliseconds, the integer, divided by 1,000, the integer, and 5, the integer, divided by 1,000, the integer, in Arduino world gives you an integer answer, and 5 divided by 1,000 as an integer goes to what? 0. So then this whole thing is 0. So what do I have to do? I've got to kind of force floating point math. So if I say take this integer and divide it by the floating point number 1,000 by putting a point, by putting a point, by putting a point. Now the 360 isn't going to hurt because that's going to make the number bigger, but just for good measure, I like to kind of force I like to force these things to be floating point numbers just so I'm not surprised. And so that's what I usually do. If there's any doubt when I'm doing Arduino coding, I will force floating point math by putting those points in there. So now let's see what happens. Let's run this thing. Now after that big show off thing, probably I've got another error in here. I really hope it's not still 0 this time, okay? I hope it's not some other just silly mistake in there. But now we're going to call this up. Okay, now watch this. I'm going to come and look at that. What did I do? In yaw, blue, I went to minus 90, and then I go back to 0. I go to like plus 90. I go back to 0. And so what am I seeing? I am seeing yaw, right? I'm seeing yaw. Now look at this, the orange. What am I seeing? I'm seeing roll. Do you see that? I'm seeing roll. Now watch this, pitch and pitch. Okay, what am I seeing? And watch this, pitch. You see it stays up. Now you can see the transient signal, but then you can see pitch is up. So I've got roll, I've got pitch, and I've got yaw. Right? Do you see that? Now, let's hit the button. What do we love? What do we love? We love the fact that this doesn't have any noise. We love that it's beautiful, smooth signals. And we love, even if I shake it and put a vibration on it, even if I put a vibration on it, the gyro doesn't read vibration. But now tell me what we don't love, okay? So look at that. I start at 0, and down here the pitch is what? The pitch is off to the races. Am I changing the pitch? No, I'm not changing the pitch. But I have a what problem? A drift problem that's pretty bad. I've got a drift problem that is pretty bad. And then I'm also developing up here a roll problem. And then my yaw problem here is not quite as bad. But you see, I have not touched this thing. It's low noise. It's smooth. But what is the problem? I have a drift problem. Okay, so now let's think. Also, what do I like? I like that it's fast, right? It is very snappy. It is very fast. It does not have noise. But what does it have? It has drift. So what do I love about the accelerometer? There's no drift, but there's noise. What do I love about the gyro? There's no noise, but there's drift. So you see, it's like you can't win. It's like, what do you, and with the accelerometer, I can filter out the noise, but then I'm what? I'm sluggish. What do I want? I want to be fast, I want to have no noise, and I want to have no drift. Right now, with either one of these solutions, I can get 2 of the 3. Pick which 2 of the 3 you want, and you can get them, but you can't get all 3 at the same time. All 3, what? You want it to be fast, you want it to have no noise, and you want it to have no drift. And you see, our drift, we're already here in the pitch. We're already to 180 degrees. So this thing has told me that I've turned the thing all the way upside down already. You see, so I've got a big drift problem as much as I love the other characteristics. Okay, now why do I have a drift problem? I have a drift problem because as this thing is sitting still, I'm reading 0.04 radians per second. I have a very, very small offset error that when I'm not rotating, I'm thinking I'm rotating a fraction of a degree a second. So the X has a 0.04 radian per second offset. The Y has a 0.02. And the Z has a 0.01. And you remember when you were looking at the curve, the Z was getting off slower and the X was getting off faster. And so that has to do with these offset errors here. Okay, so we're heading towards the ultimate solution because as an engineer, what do I want? I don't want 2 out of 3. I want 3 out of 3. I want it to be fast. I want it to have no noise, and I want it to have no drift. And we're going to be moving that direction in little increments. Now, in the end, we're going to fuse the data from the accelerometer to the gyro. But remember, when we did the accelerometer, we took a first few steps just on the accelerometer to what? Reduce the noise. Now I want you to take this gyro, and without taking help from the accelerometer, I want you to see if you can try to calibrate out some of this drift problem. So get the accelerometer as good as you can, which we did using the low-pass filter. Now get the gyro as good as you can by thinking, is there a way that you could filter out some of that drift? And then in the final thing, what we'll do is we'll then combine the improved data of the accelerometer with the improved data of the gyro and see if we can get the ultimate solution. So that is your homework for next week. And I hope you guys are having as much fun taking this class as I am making it. Like I told you earlier, I have some of the patents on the first technologies that were used to manufacture these accelerometers and gyros. And so I was sitting there in the lab, banging the table, seeing if I could see an acceleration signal for some of the very first of these microelectromechanical systems for acceleration and gyros and so forth. And so brings back fond memories, and the magic is still there for me. And I hope you find some of that magic as you're playing with the accelerometers and gyros as well. Also, at this point, I always give a shout out to my Patreons. I really appreciate your support. Without your help, I would not be able to continue to produce quality, fresh content every single week. Thank you guys. You can also help the channel by giving this video a thumbs up and leaving a comment down below. When you do, also remember to subscribe to the channel, and then most importantly, share this video with other people, because the world needs more people thinking like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.